So on the other side now, what do we have? We have the AC. So the grid is what we're connected to, and the grid is basically a voltage source operating at a fixed frequency. So in Europe, you'll get a 230 volt AC standard 50 hertz. That would be a standard interconnection for a residential installation, single phase, so line and neutral. In US, you have a so-called split phase installation where you have 220 volt line which are out of phase, 180 degree out of phase from each other, and that's so that this way you can have 120 volt outlet in the house and 240 volt outlet in the house if you go line to lines from one extreme to the other. Our microinverters are connected to the two lines, so we need 240 to connect our unit. In Europe, we connect to line to neutral because it's about the right voltage. It's nice for us to work at higher voltage. You know, we could do an inverter for 120 volt, but you have less line loss when you run at 240, so it's actually cheaper to do it this way. And of course, you can have three-phase systems. I drew there 120 volt, 208, so it's 120 volt line to neutral, 208 line to line, typical three-phase system for a United States smaller installation. Bottom line is for transmission distribution, the higher the loss, the higher the voltage, the less losses are in line with a given wiring. So again, typical specs in US on the grid, 120 to 40 single split phase for residential and low voltage. Commercial low voltage would be 120 to 8. Industrial low voltage would be 277 480, 60 or three phase. So 277 is line to neutral, line to line would be 480 volt. Medium voltage distribution, 12.5 kV, three phase, fairly standard. In Europe now we have 230 volt 50 hertz single phase, or three phase will be 230 400. Okay? Of course the ratio between the two numbers is square root of 3, so it's because of 120 degree phase shift. So what standards do we have to comply with now? We have a lot of standards to comply with. Sure. I'm sorry? So our standard unit works either in 240 split phase or 208. And in 208 meaning that we will connect a unit to two of the three phases. So we only do single phase systems, either connected line to line in a split phase installation at 180 degree apart, or 208, 120 volt line to ground, line to neutral in 120 degrees apart. So we have single phase inverters at this point. Now there is actually an interesting trick, which is that on 208 installation or even 480 installation, what we do is that we have a cable which have all three phases in the cable, and every connector we take out two of the three phases and we rotate every time. So this way you pick L1, L2 on the first, L2, L3 on the second, L3, L1 on the third, and it self-balances the system out. So we can do balanced three-phase installation with single-phase inverters without any design, or it's really brainless. So why would we do this? Well, we will do this because the beauty of a three-phase system is that you don't need to circulate a neutral current for nothing. In a three-phase system, you basically don't need the neutral if everything is balanced right. So you eliminate the return loss, the loss of the return current. You inject current power on all three phases, and the return magically disappears. So you don't have any losses in the return, which means that it's basically half the line loss on the copper system. Okay. Back to standards. We have to comply with National Electric Code. With National Electric Code was designed under the direction of basically insurance companies, and it's designed to make sure that regular installation, whether they're industrial or residential, are safe. So they define what wiring can be used, what type of wiring system you can use. It's actually quite complicated. The book is that thick. As far as safety, we comply to standard called from UL, Underwriter Laboratories, which is UL standard 1741, which describes exactly what tests should be done to make sure that the inverter is built in a safe way and will not present a risk to the users. So that's not done. We're not done there. We still need to go to interconnection standards. Now that we have a safe product, it doesn't mean that we can interconnect to the grid. So there is an IEEE standard called 1547, which says exactly how the inverter should respond to overvoltage, undervoltage, off frequencies behavior, and so on and so forth. That's for the low voltage side. On the medium voltage side, we will have to comply with the standard called FERC 661, which is also does a similar type of requirement for at the medium voltage level. We have to comply with electromagnetic emissions. So that's called the Federal Regulation 47 Part 15, which defines how much energy we can spew out as a conducted or radiated through the line or in the air. And we have to comply with surge testing. That's a pretty interesting test where we have to put a pulse in a unit while it's running of up to 6,000 volts and 3,000 amps. It's a little box like this, and we put quite a bit of energy in there. It doesn't last very long, but it's enough to make a lot of damage. So, and the funny part is that whether it's a microinverter, which is only rated for 250 watt, or whether it's a megawatt inverter, it's the same test, which is not too fair. But but anyway, that's life, and we have to do that. Funny enough, there's an interesting anecdote on this, is that the reason this test stopped at 6,000 volt is because it's actually a very old standard, and they did a whole bunch of surveys in houses and industrial location and all that. And what they found is that when the voltage exceeds 6,000 volt, all the outlets start arcing. So there's no point in going higher than that because it's self-limiting, basically. So our box can take that and no more. All right, so the grid. Well, it's really nasty. As I said, we have to comply with short duration pulses, but we also have to comply with all kind of bizarre events that happens all the time. When we first introduced, when I first units and I put them on my own roof, they would basically blow up every morning at 8 a.m. And we're like really surprised. How is that possible? What's happening at 8 a.m. that blows up all my units? And it turned out that there was a waveform on the left there where at 8 a.m. the substation was connecting reactive, basically capacitors for reactive power control. So at 8, they turn on a big, huge relay, and they connect huge amount of capacitance on the line to optimize the voltage on the line. And every time this happens, it's pretty ugly, as you can see. And we had a little bit of a weakness that basically blew it up. So it took a while to figure this out. But anyway, it's life on the grid. We had to actually gather data from a lot of locations to be able to bombard our equipment with our inverter with similar type of waveforms to make sure we don't have any weakness. So we have a huge database of waveforms. Do other people? I'm sorry. So yeah, it's a good question. I assume why other appliances take that. Well, if you look at most power supplies, usually on the front end you have a diode bridge, and then you have a capacitor, either directly or indirectly behind an inductor. And this big capacitor is really good at actually absorbing some of these problems. Well, in a DC to AC conversion, we don't have anything like this that self-protects the unit. So it makes it harder. And the other piece is that we have to inject current on the grid at very precise timing. That means we need to control exactly what is the shape of the current going out of the unit, rather. And the original design I had was a little bit sensitive to error in timing, and would create a weakness in there. But the truth of the matter is, it's really nasty out there. You can see on the right-hand side, here's what happened is that this was a working location. That's also some waveform we picked up from the field. And everything was fine, and all of a sudden, you see not only a very fast reduction of voltage, but you see that there was a huge phase jump, actually, from the first half cycle to the next half cycle. And that happened because it was at the end of a three-phase transmission line, and one phase was lost. And when that happens, it changes the instantaneous phase shift on the voltage. So you have to take that too. You don't expect, well, usually it's 60 Hertz, but sometimes you have some interesting behaviors, and you have to be able to test for all this. At this point, we have, many thousands of millions of hours of operation. So we know we can do that pretty well. We rarely have a problem created by a grid issue. Okay, so when we have now a microinverter, it's between the PV and the grid, so it's geared up for one type of module typically and one type of AC port. And the microinverter is mounted on a rack, whereas a PV module is mounted. Okay, so what are the functions of the microinverters now? Very important one is MPPT, maximum power point tracking. We need to constantly find and operate the inverter at the sweet spot, at the maximum power point. There are hundreds of papers on MPPT algorithm, hundreds. It's a very interesting problem, which is not that hard if you look at it the right way. It's not that hard to solve. We actually came up with our own, but there are many working solutions for this. Speed and accuracy are important. Usually the problem is if you try to be too fast, you end up having a lot of dithering, and the static accuracy won't be as good. If you are too slow and more accurate, then when things start changing, you start losing energy. So there is a nice compromise to be found between speed and accuracy on this parameter. MPPT accuracy is just as important as power conversion efficiency. For some bizarre reason, the industry has been totally focused on power conversion efficiency and totally under-focused on MPPT accuracy. But they are just as important, so we treat them both the same way. So on top of that, where we report the DC voltage and current that's operating at a given time. So we can indeed figure out what's going on with the module. Is it shaded? Is it broken? Is it soiled? So on and so forth. And the other piece is that we need to check for arc faults as well. Every inverter now have to do this. Look to see if there is an arc fault going on. AC side, well, we need to synchronize to the grid, so we are slave to the grid. Before we turn on, we have to listen to the grid, say, well, what phase are you at? Is the voltage okay? And we need to lock up to that, and before we're ready to inject current, we have to be exactly in phase and sure that the grid is okay. With inverters, there is an interesting problem, which is that if you have an inverter that is connected to the grid, and across the grid there is a load that matches exactly what the inverter is doing. So you put out 200 watt, for instance, and the load is exactly 200 watt. If that's the case and you actually disconnect the grid, the system will keep operating forever until something changes. So that's really a bad thing, because if you have somebody doing some maintenance on a system, takes the grid off, expects that everything will go off, and by really bad luck, there is a local load that matches exactly what the inverter is doing, its power is still there, and people could be killed. So there is a very difficult test, quite difficult test to me, which is that test agency, part of 1547 test, looks for this islanding condition, duplicates that. We have to prove that we can island, and then we turn on the algorithm, and we need to disconnect within 2 seconds. These tests cannot be done in a passive way. I cannot just look at voltage and frequency and say, I'm islanded. It's not possible. You have to actually actively disturb the situation, kick the thing, and see how the system behaves. If you are connected to the grid, things are very stiff because the grid will impose a voltage no matter what. If you are on an island, you can kick it and things will move. And you have to, that's a typical way to figure this out. It's quite a tricky algorithm to get right. Sorry. Okay, power conversion now. DC power, for instance, 25 volt 8 amps is transformed into AC power. For instance, 240 volt RMS, 0.83 amps. So you have blue line is DC power coming in. The gray line, kind of spiky line for some reason, is the AC power going out. Well, right there you see you got a little bit of an issue, is that one is flat and the other one is pulsating. So bottom line is any single phase inverter have to have some kind of energy buffering system that can store energy when you get more DC power in than AC power going out, and retrieve that when the AC power is high and the DC power is still the same. So that's a function that's inherent to any DC to AC converter, or for that matter, any AC to DC converter on single phase. It's interesting to see that three-phase devices, not only they don't have loss and a return line, they also don't have that problem, because if you look at the sum of the power in all three phases, it adds up to a DC power. So you will need to have this storage, this energy storage system in a three-phase system, in a three-phase inverter. So those are archetypical technologies to do the power conversion system. Top one is the most common one, the most traditional one, I would say. It's a dual stage inverter. So first stage is a booster, which takes DC in from the module, boosts it up to a fairly high voltage, so there's 400 volt or so. The capacitor there is an energy storage mean. And then you have a very simple, usually two-leg four-switch voltage source inverter on the output that takes that 400 volt DC and makes 230 volt AC out of it. Fairly simple, easy to control. The second topology is different. We have the capacitor is right at the input. It's actually a larger capacitor than the one before. And then we have a stage that does boosting, but does shaping as well. So the output of that stage is a rectified sine wave. Okay? And then the only thing we need to do afterwards is to have a switch matrix which can do the reverse of the diode bridge and either go right through or inverse the voltage. Just you go through or you swap. Okay? And when you do this, you get your sine wave output. So that's the topology we've been using to begin with. This we're still using now, actually. This approach allows to have a much higher efficiency than the previous one, because on the first block diagram, you process energy twice in a fairly intensive way. So the booster has losses, the inverter has losses, and they're both about the same. And if you get 97% on the first stage, you're really good. If you get 97% on the second stage, you're really good. So you end up at 94%, 95% range. Okay, conversion efficiency-wise. The second one, I can get 96, 97% on the first stage, and the second stage is really 4 switches running at 60 hertz. It's super easy to do that. So, and the losses are extremely small because there's no really switching losses there. So we get 96, 97% on the first one and over 99 on the second one. And because of that, it's actually a superior solution. Third one, that's kind of the dream thing. It's a true single-stage inverter where you have a buffer and a DC to AC conversion in one shot. And of course, we're working on that.